Okay, let's have a look at this one. So we're looking for the force that B exerts on A. So our best bet here is to break this system up and look at what forces I have versus what forces I can calculate. Okay? If I am looking at box A, there's the applied force from the person pushing to the right, and then there would be a force of friction opposing to the left. But I'm not told either one of those. Can I use, oh, I'm sorry, there's another force acting back on A. What is it? B, yeah, the one I'm supposed to find. Can't believe I almost forgot that. Okay, so force of B on A. So there's 3 forces acting on box A, and I don't know any of them. Okay? That means there is 0 way for me to use box A to finish this question off. Right? It is just useless because I don't have enough information. Instead, I can look at box B. Right? I know that box B is 15 kilograms. I know it's accelerating at 1.3 meters per second squared. What can I calculate right now? F net, yeah. I can calculate F net, and I should probably do that because I'll probably end up needing it. Okay, so mass times acceleration. What does that come out to, guys? I forgot to fire up my calculator. Sorry, what? 19.5? Newtons, and that would be to the right because the acceleration was to the right. Okay, forces that are acting on box B. What's that force? F of A on B, right? How does that relate to the one they want me to find?
Because they're the same but opposite.
Same but opposite in direction. That's the action part of the action-reaction pair. I'm looking for the reaction force. Okay? The other thing they tell me is that there's a force of friction that is resisting box B, and they tell me that it's 9.5 newtons. All right. Since I know one of the 2 forces, and I know what they add up to, can I find the force I'm missing? Yeah, so just like we always do, I've done M times A. Now I'm going to go F net equals the force of A on B plus the force of friction, and I'm just going to subtract the force of friction over here. So I'll have F net minus force of friction equals FAB, and that's going to be 19.5, right, minus negative 9.5, because the friction is the other way, right? When I do that, what does it go out to, 29? Yeah, rounds to 29, because we only have 2 significant differences. Okay, so it's going to come out to negative, this one will be positive, 29 newtons, but the force I'm looking for is the action-reaction pair, so the force of B on A will be negative 29 newtons. Actually, not negative, 29 newtons left, because I was given right and left in the question. All right? Expect to get something like that on your unit exam as a Newton's third law question. Okay. All right, yesterday I didn't get a chance to show you some funny Newton's third law videos. Okay? How many people in here have ever used a firearm of some kind? All right. What do you have to be mindful of besides the dangerous end? Recoil. What's responsible for recoil? Newton's third law. Okay? Every action, that is the gases pushing on the bullet, has an equal and opposite reaction. The bullet pushes back on the gases, which pushes back on the firearm, which then, of course, leads to it hitting you if you're not properly braced for it. Okay? So that ends up looking a little bit like, well, if you're kind of dumb, like 4 rolls. So what we go over today is going to be pretty much review of work energy theorem from Science 10. Okay? In Science 10, when you did work energy theorem questions, you were like force times distance equals the change in kinetic energy, or force times distance equals the change in potential energy. And that's, of course, still going to be true, but in Physics 20, it's not always kinetic or not always potential. It could be both. Okay? Because the strict definition of work is that work is a change in mechanical energy. How do we calculate mechanical energy? What two things do you have to add together to get something's total mechanical?
Kinetic and potential.
Kinetic and potential. So when you do work, it is possible for you to change both of them. Okay, you could change the object's potential energy and the object's kinetic energy. Like for example, if I were to throw something up into the air, I would not only make it go faster, but I would also make it go higher. Okay, the work I do could change both its kinetic and potential energies if I'm accelerating it upwards, right? Okay, so work's a change in mechanical energy, and you do work provided you exert a force through a object, on an object, through a, starts with D, force times distance. Yeah, if you exert a force through a distance, you do work. Okay, right now, I'm exerting force. Am I doing any work? Is the wall's energy changing? Then I'm not doing any work because there's no distance. There's no change in position of the wall. Okay, I don't do any work on the wall because I'm not changing the wall's energy. I can exert a force on it all I want. Okay, but I'm not going to change or do work on the wall because the wall's energy won't change. Oh, put a Mr. Dickey on. Just say hi. Oh, Mr. Baldwin has them now. Okay. Is that sort of making sense? Work is force times distance. You have to make something move if you're going to change its energy, right? You're going to make it either go higher, that would change its potential, it's got to move for that, okay? Or you're going to make it go faster. Again, it's got to move in order for that to happen. So for work to be done, energy has to change, kinetic, potential, or both, and the object's got to go somewhere. Okay? You can't do work on it if it isn't going to move. Okay? All right, so work is both force times distance and change in mechanical energy, okay? Which we could say would be final energy minus initial, right? Change is always final minus initial, okay? Okay, everyone with me on that? Is that ringing a bell from last year? Okay. All right, so the relationship between force and work should go something like this then. If I use more force over the same distance, I'll do more or less work. If I use more force over the same distance, will I do more or less work? More. Okay? I mean, think about it. If I, if I pull this desk with 2 newtons worth of force, it accelerates a little bit. If I pull it with 5 newtons worth of force, it accelerates a lot more. Agreed? I change its kinetic energy by more if I pull harder. Okay? So the relationship between force and work is direct, okay, or directly proportional. If I double the force, I'm going to double the work, provided the distance stays the same. Okay? All right. And then this part here is just the whole work is a change in mechanical energy ID. Okay. Anybody ever had to push a stalled car before? All right. Did you start it that way? Okay. That you used to be able to do that a lot more. When standard transmissions were a lot more common, you could actually start a car by pushing it. And you can't do that with an automatic unless you can push it to more than 30 kilometers an hour and you're willing to slam it into gear, which is generally not good for it. Okay. But with a standard, you could get it rolling, put it in second, and then pop the clutch, and it would start because the pistons would be moving up and down and start a compression. Okay? You had to give it enough energy, though, for that to work. Okay? In other words, you had to do work. Yeah, you had to exert a force, push, through a distance, get the car moving. Okay? And when you did that, you would increase the kinetic energy of the car, which could then be used to start it without having to use the battery. Usually the battery was dead, that's why you had to do it. Okay? All right. In this picture, the person is pushing the car to the right. Okay? So what direction would the work be?
To the right. To the left.
work is actually a scalar quantity. Okay? Force and distance are the two things we use to do work. We multiply them together. But work is scalar, as is energy. Okay? We can't give work a direction because if I change the energy of something, that energy could be kinetic or potential. There's no direction on that. It's like if you eat food, you don't say, oh, well, I consumed 2,000 joules worth of energy south. Right? Your body's going to use that energy to do whatever it wants. It may be in many different directions. Okay? Energy and work don't have direction. Now, that said, work can be positive or negative. Does that seem contrary? I just said work is scalar, but then I said work could be positive or negative. Is it okay if I do that? It is. The positive or negative doesn't convey direction. It conveys gain or loss. Okay? From my perspective, if I do work on the desk, from my perspective, that's negative work. I lose that energy. I transfer it to the desk. Okay? If the desk hits me and makes me move, that's positive work. Okay? Now the work was done on me and I gained the energy. All right? Everyone kind of follow the difference there? Okay? So it's not going to be directional. You're not going to say I did 10 joules of work east. Okay? You'll never say that because work is scalar. But you could say the work done by the mass is negative 10 joules, implying that it gave it to something else. Okay? All right, so work does not convey directional information and is thus a scalar quantity. All right. These ladies here, they're pushing on that rock. Are they doing any work? No. No, rock's not moving. So its energy isn't changing. Work's a change in energy. Okay, whole purpose of that picture, work is a change in energy. No matter how hard you push, if the object doesn't move, you don't do any work on that object. Okay? Everyone all right with that? Okay, then why do you get tired? If they push on that rock all day, they're not going to do any work on the rock. They're going to get tired. If work's a transfer of energy or a change in energy and they didn't change the energy, why are they tired?
You're still exerting force.
Yeah, and it's exerting it back on you. Now, that does do work on you. Okay? If you push on something, okay, do your muscles get shorter? Right? In order to exert force with your muscles contract. That's the distance over which the force you're bracing against, the reactive force, does work. That's why you get tired. You have to brace yourself against the return force that is produced back on you because of Newton's third law. Okay? So you get tired because it's actually causing you stress and using energy to maintain your position, shortening your muscles. Okay? All right. Okay, but you don't do any work on the rock. Okay, something we didn't learn about in Science 10. Okay, in Science 10 we just said that force times distance equals work because we didn't do any vector stuff. What if, like in this situation here, the person is exerting a force in a different direction than the object moves? Okay, does all of that force do work? It doesn't. Okay? Look at it from this perspective. Okay? The luggage carrier is going to go this way. It'll probably accelerate, okay, in that direction. So that'll be a change in what kind of energy? Kinetic, because it's speed, right? Kinetic deals with speed. So if she pulls it this way, this part of the force changes the kinetic energy of the luggage carrier, the horizontal component. But here, there's also a vertical component. But does the luggage carrier move vertically? If it doesn't move vertically, then there's no vertical distance for that force to work on. You're not lifting it. You're not changing its potential energy. You're not changing its kinetic energy. So this entire force doesn't do work, only this part of it. Okay, so we kind of have to match it up and go, okay, they may have pulled it this way, but it didn't go that way. So I can only use the part of the force that actually did something to calculate how much work was actually done. Okay, so if you look on your formula sheet, you'll actually see that the formula goes work equals F cos theta D. Okay. So the cos of theta part just takes into account that you might be using only one component of that force because only part of that force actually did any work. It doesn't come up very often. We just have to illustrate it to you that that could be true.
Could it come up on like a quiz?
Not this week, and I don't think ever, actually, but I'll double check. Okay, we just have to know that if the energy isn't changing in a certain direction, then the entire force may not be doing work. Okay, everyone all right with that idea? Okay. We only use the force that's actually causing something to happen. Vertically, nothing's happening. Okay, so there's no work done vertically in this situation. Okay. All right, so this would be a situation where we would use the cos of theta thing, just so you see it done. Okay, so the force is directed 45 degrees from the horizontal. Or sorry, it's 45 newtons, sorry. Okay, so there's 45 newtons worth of force, okay, and it's a 50-degree angle. Right? This is the only part of the force that's actually doing any work. The box isn't moving, or the luggage carrier isn't moving vertically. So if I want to calculate the work done, if she pulls it 75 meters, then I go F cos of theta times D, so that'll be 45 newtons times the cos of 50 degrees times 75 meters. Okay, so 45 times the cos of 50 times 75. Oops, I did that wrong. Cos 50 times 45 times 75. No, actually, I didn't do it wrong. Okay, so that's how much work she does. 2.2 times, or actually we got 3 sig digs there, so 2.17 times 10 to the 3 joules. Okay? Does that sound like a lot of work? It's a fair amount of energy, it's a fair amount of work. Okay, it's probably pretty heavy. Do you accelerate the whole time when, like, if you're pulling your luggage behind you in the airport, are you constantly accelerating? Okay, so what if she pulled this thing at a constant velocity? According to that, she still did work, even though if it's moving at a constant velocity, its kinetic energy doesn't change. Is she still doing work then? She doesn't change its potential, she doesn't change its kinetic, but she does 2.17 times 10 to the 3 joules of work. How is that possible?
Because she's moving.
She's moving, and is there anything resisting her? What might be resisting her?
The ground,
Yeah, a force.
friction.
Right. Like, if something's got friction, what does it usually produce? Heat? Sound? Are those forms of energy? Would they be evidence of the 2.17 times 10 to the 3 joules of work she does? Okay, so you can do work without changing the energy of a specific object. You actually end up changing the energy of its surroundings. You do work against friction, and that turns into sound and heat and light. We don't deal with like mathematical situations where that's involved, okay? But we do look at it as that is evidence of work, okay? It's just turning into non-useful forms of energy, okay? It's not changing the energy of the luggage, it's changing the energy of its surroundings. Okay. Bench press. So you've got this big 710 Newton barbell, okay? So what is that, 150 pounds, something like that. Okay, it's heavy, okay? And you're bench pressing it, pushing it upwards. Okay, do you do work when you push the barbell up? Okay, the barbell's energy changes, right? Okay, if you push it up at a constant velocity, are you still doing work? Yes, because you're changing its potential energy. Okay, so that counts for work. Okay, you've now lifted the barbell, and now the barbell has potential energy. It has the potential to do work, so don't drop it. All right, because if you do, that potential energy will turn into kinetic, and the work it will do will be crushing your chest probably. Okay, so you want to leave it and hold it there or put it back on the rack. Okay, when you lower it back down, what happens to that energy? What happens to the energy of the barbell?
It would transfer back to you.
Yeah. If you're going to lower it, do you still have to exert just as much force as you did to raise it? You do. Okay? This is what people do wrong in the gym. Okay? They're like all about the pushing the barbell away and then they just kind of let it come down. You're supposed to resist it coming down and push it going up. You should work just as hard to lower the barbell as you do to push the barbell up. Okay? But lots of people, they get it to the top and like, and then they hope their spotter will grab the bar. Okay? You're getting only half of the workout if you do that. Okay? You want to maximize your gains, then you want to lower it slowly, raise it slowly. Okay? That way you allow it, you have to resist it coming back down and you do twice as much work. Okay? Now, how can we prove mathematically that the barbell gains energy on the way up and loses it on the way down? Okay? Here's our formula, right? Work is F times the cos of theta times D. Okay? Now, do I know the force? What is it? If I want to push the barbell up at a constant velocity, how much force up do I have to exert? 710 newtons, right? Constant velocity means it won't accelerate. I have to push with the same amount of force that gravity pulls on it with. So I would exert 710 newtons worth of force. What's the angle? I'm pushing the barbell this way, and the barbell is also going that way. Is there any angle between the force and the distance? Okay, so the angle is 0. What's the cos of 0? 1. Okay, so cos is 0, so 710 times 1, which we wouldn't bother to write, okay, times 0.65. All right, so 710 times 0.65. Okay, so this person does 462 joules worth of work to lift the barbell. When I lower the barbell, I still have to push which direction? Up. But which way does the barbell go? How many degrees are there between up and down? 180. What's the cos of 180? -1. Is that going to make sure that the work done by the barbell ends up being negative? Because you're going to have 710 times the cos of 180, -1, times 0.65. Okay? So it'll come out the other direction. Okay? The barbell will lose that energy, and that will do work on you as it comes back down. Okay? Everybody all right with that? So that's that positive, negative work idea that I was talking about before. Okay? If you do work on the barbell gains energy. But when the barbell comes back down, it has to give it off. Okay? It's either going to turn into, kinetic energy. If you dropped it, that would be bad. Okay? Or it's got to be absorbed by you by lowering it down, doing work in the other direction and taking that back on. Okay? All right. Questions there? Okay. Okay, so work energy theorem is what we wrote mathematically on the board here before, okay? That work is a change in mechanical energy, okay? And that mechanical energy is obviously the sum of kinetic and potential, okay? And that work is also force times distance. You did all kinds of problem solving with this in Science 10, where you went, work's a change in kinetic energy, and then you went force times distance equals 1/2 mv squared, and you solve for something. Okay, those were your like Science 10 level work energy theorem questions. Okay, we're still going to work on the same principle, right? But now we're going to look at this as though it's a mechanical energy situation. Okay, so we're going to say work is still a change in energy, but now it's going to be final minus initial. Okay, and it was in grade 10 as well, right? It was just only one type. Now we're dealing with a change in mechanical energy. Okay, so what that means is this. The final mechanical energy would be like this. Potential energy final plus kinetic energy final minus potential energy initial plus kinetic energy initial. Okay, that's what mechanical energy is. It's the sum of your potential and kinetic energies. Okay, everybody all right with that so far? Okay, I'm gonna give you about a 3-minute break here before we start looking at any examples, okay? Because I'm talking, so give you guys a little break within the classroom here, okay? And then we'll talk about some applications of this here. Okay, so in this situation, they're asking us to calculate how much work is being done. Are we sure work is actually being done here? Okay, so we're starting at the bottom of this ramp and we end up at the top. Okay, so what kind of energy is changing? If we start at the bottom and end up at the top. Potential's changing, and the kinetic is also changing because they tell us at the bottom it's only moving at 1 meter per second, but at the top it's moving faster. Okay, so whatever's happening here, this applied force, it must be pretty big. Okay, because it's not only changing the kinetic energy from 1 to 4, it's also pushing it up the ramp. Okay, and if you go up, you increase your potential energy. If you speed up, you increase your kinetic energy. What if the speed decreased on the way up the ramp? Would we be doing work then? Maybe, it's possible, okay? But if the speed slows down and it comes to a stop at a certain height, then the energy would be conserved, right? All the kinetic it had at the bottom would get turned into potential at the top, and no energy would change. That would be more of a conservation of energy question. In this one, we're sure. There's definitely work being done because not only does it go up the hill, it goes faster up the hill, okay? That means both types, kinetic and potential, are changing. All right, so that's something we have to establish just from looking at the question. Is work actually being done? All right, we're sure it is, so we're gonna say this. Work is equal to the change in mechanical energy, okay? It's also equal to force times distance. But I can't use that here. Why not? Why can't I use force times distance in this question?
We don't know the force or the distance.
We don't know the force or the distance. I can't use it because I don't know either one of those things. Okay? They never tell me how long the ramp is, and they never tell me how hard the box is being pushed. Right? So I can't use force times distance here. But I can calculate the change in mechanical energy because I can calculate, okay, final potential, I can calculate final kinetic, and I can calculate initial potential and initial kinetic. Okay, that's going to calculate the change in mechanical energy, right? Final minus initial. Okay, can I make my life a little bit easier here if I look carefully at the situation? Are any of those four energy types zero?
The initial potential is zero
Why?
because it starts at like ground level.
Right, it starts at the bottom of the ramp. You can't fall any further, okay? You don't have any potential energy, okay? Remember that potential energy is mass times acceleration due to gravity times height. You don't have any height, you're at the bottom of the ramp, right? So you don't have any potential energy initial, so I can save myself a little bit of time and not have to worry about that number. Okay, so I want to calculate how much work is done. So I'm going to put in m times g times h final. That'll calculate my final potential energy. Okay, I'm going to add that to my final kinetic energy. Okay, so I'll use 1/2 times the mass times the final speed squared. And then I'm just going to subtract from that 1/2 times the mass times the initial speed squared. And that should give me the change in mechanical energy. Everybody all right with my reasoning there? Okay, are those formulas ringing a bell from last year? mgh and 1/2 mv squared? All right, pretty sure we know all of these numbers, right? They told me that the mass of the block's 1.2 kilograms. They told me the final height was 0.850 meters. They told me the initial speed was 1 meter per second and the final was 4. Okay, so let's put in our numbers here. 1.2 times 9.81 times 0.850. Okay, that's going to be my final potential energy plus my final kinetic energy. 1/2 times 1.2 kilograms times 4 squared. That'll be my final kinetic. Okay, I'm just going to bracket that. That's my final energy. Minus my initial energy, which is all kinetic because we're at the bottom. 1/2 times 1.2 times 1 squared. Okay, questions on what I've done there? Okay, so let's plug all that in and see what we get for a number here. All right, so 1.2 times 9.81 times 0.85 plus 0.5 times 1.2 times 1 squared, okay, minus 0.5 times 1.2 times 1 squared. Oh, that's supposed to be 4 squared there. Good thing I caught that before I did anything else. Okay, so I get 19 joules, and it's positive. That means that the energy is increasing, right? The work is positive or negative? From the box's point of view, the work is positive. It gains 19 joules of mechanical energy by accelerating up the ramp. Okay? Everybody all right with what we did there? This is work energy theory. You did stuff like this last year when you just did work equals final potential energy. Okay? This is just now doing full mechanical energy problem solving. Okay? The principle is still the same. Work is still a change in energy. Force times distance is still work. It's still a change in energy. We're just adding in a couple of other things. Okay? So as long as you understand that part, okay, the work is a change in energy, and that you're able to tell when certain types of energy change, the rest is just algebra. You guys are good at algebra, so the math isn't gonna challenge you, okay? What's gonna be, the hard part is looking at this and going, oh yeah, not only is it higher up the ramp, which means potential energy changed, it's also going faster, which means now it also has more kinetic energy. That means positive work because it went and did that. Okay, that's the kind of analysis you have to be able to do when you look at a question. Okay, anybody need that anymore? Okay, I would like you guys to try 1 and 2 on there, please. Okay, they're pretty straightforward, okay? You don't have to do the cosine theta thing on either of those, okay? So just try 1 and 2.
What is the units for
Joules, J, just J, yeah. Oh, we forgot to talk about units. Real quick here, guys. Okay, when you multiply force times distance, you're multiplying kilogram meters squared by meters. Okay, so that gives you a kilogram meters squared per second squared, which is a Newton meter, or mercifully, a joule. Okay, you only ever have to write joules, but just so you know where those units come from, a joule is technically a kilogram meter squared per second squared. Okay, try 1 and 2 there, guys. Okay, so they want to know how much work is done on the climber by the rope. How many people have ever rappelled before? How many people ever got rope burn before? Okay, rope burn is because of this. Okay, if you were going down the like rappelling down and you didn't have gloves on, okay, you would burn your hands because you'd be trying to convert the mechanical energy of your fall into, using the force of friction to turn it into heat, just like your brakes do when you apply them in your car. Okay, they turn your mechanical energy into heat. Okay, if you've ever climbed, you know you don't touch your carabiner. Okay, that's the thing that the rope goes through after you've done a bunch of rappelling, because the rope has been going through there, rubbing on it, and converting your kinetic energy into heat. That's what saves your life. Okay, so you want it to do that. The work is going to be the change in energy between the top and the bottom. Do you want to have the same amount of energy at the bottom of a cliff as you do at the top? No, because that means you fell. Okay? If you have the same amount of energy at the bottom, it's because energy was conserved. No work is done, and you have now all of that potential from the top of the cliff is kinetic at the bottom. That is going to change your shape in an undesirable way. Okay? You want something to slow you down, a parachute, a ramp, a rope, okay, to make you go slower. So, we know that work is a change in mechanical energy. Now, at the top, we're not moving. Okay, so even though it's technically like final potential plus final kinetic minus initial potential plus initial kinetic, are any of these 0? 2 of them are, yeah. How much kinetic energy do I have standing at the top of the cliff? None. Okay, so my initial kinetic energy is 0. What's my final potential energy? 0, because I'm at the bottom of the cliff, right? So now I can simplify that down to this, okay? 1/2 mv final squared, my final mechanical energy, minus m times g times h initial, my initial mechanical energy, okay? Just so happens that at the end, all of my mechanical energy is kinetic, and at the beginning, all of it is potential. All right? So, if I plug in my numbers, 1/2 times 72 times 5 meters per second squared, okay, minus 72 times 9.81 times, how high was the cliff? 25 meters. Okay, so 0.5 times 72 times 25. Okay, minus 72 times 9.81 times 25. Whoa, yeah, okay. Why does that come out negative?
Because you lost a lot of energy.
Yes, thankfully, you lost a lot of energy as you were going down the cliff using the rope, okay? You would have heard the rope hissing through the carabiner, through your gloves, okay? Sound is a form of energy. Some of your initial mechanical energy was turned into heat and sound, and as a result, you were moving at a speed your body could handle when you got to the bottom. You had less mechanical energy because you allowed it to be converted into other forms by work on the way down. Does that make sense? Yeah? Okay. All right, so question number 2. How many people have done number 2? Okay, I'll give you a few more minutes on number 2 here. There's a couple of pretty important relationships that are kind of maybe hopefully aha moments when we go over number 2 here. Okay, so for number 2, our givens are the force. Okay, so we know that a force is acting upwards with 150 newtons. We also know the distance. Okay, it's 5.0 meters up. That would also then be our change in height, or our final height, because we would assume it happened from the ground. Okay. How can I calculate the work with those givens?
Force times distance?
Yeah, that would be the quickest way. I have force and I have distance. Okay, that would be the most logical way for me to do it on this question. So work equals force times distance. So that'll be 150 times 5. Is that 750? Yeah. Okay. That's okay. So I've done part A. What kind of energy am I changing in this? Changing potential energy? Okay. Is that all I'm changing? Yeah. I'm actually also going to change the kinetic energy. How do I know that?
Mechanical energy is work, and mechanical energy is potential plus kinetic.
Right, it's potential plus kinetic. Now, if I just did this, I might accidentally assume that all of that work went into changing the potential energy of the block. Okay, but here's the thing. The change in the potential energy is going to be m times g times h final minus m times g times h initial. Well, that's 0. So if I punch this in, then I better get 750. I better if that's all I did, but I'm not going to. Okay, I'm not going to get 750 here. I'm going to get, the mass was 9 kilograms, okay, times 9.81 times 5 meters. Okay, that definitely doesn't come out to 750. It only comes out to 442. Or sorry, 441. We have 3 sig digs there, right? 441. Okay, so I did 750 joules of work, but only 441 of them were required to change the height by 5 meters. Where'd the rest go? Kinetic. Yeah, so not only did this thing rise, it accelerated upwards. Okay, so could I calculate how much the kinetic energy changed? Okay, so we've done A and B now. Okay, they want to find the change in the kinetic energy. Well, the change in kinetic energy would just be 750 minus 441. Okay, so if I do that, Okay, 309 joules. Okay. Number 3 is going to ask about this, but I'm going to ask it differently. If the kinetic energy changes by 309 joules, we just said that that means the object's going to not only rise, it's going to accelerate. What kind of force do you need in order to make something accelerate? A net force. So that 150 newtons was more than I needed to raise the mass. Agreed? Okay. How much force did I need to raise the mass at a constant velocity?
141.
Oops, sorry, that's supposed to be joules. Okay, so is this essentially an elevator? Okay, so I've got this mass here that's 9 kilograms, okay? Can I calculate that force? That's force of gravity, right? If I want to raise it at a constant velocity, then this force and this force are equal. Okay, so if I take that 9 times 9.81, right? That's how much force was required to lift it at a constant velocity, 88.29 newtons. Okay, so what's my net force then? I used 150 newtons to raise this. Gravity's only 88.29. What's my net force? Right, I just have to subtract the 2, right? Okay, if I go F net, okay, equals the 150 minus the 88.29, right? Okay, so that's going to give me this number, right? Come on, calculator. Okay, so there's my net force. Multiply that by 5 meters. Force times distance. What do you get? Do you get the change in kinetic energy? Okay, if there's a net force, there's going to be a change in kinetic energy because net forces cause objects to accelerate. Okay, so that's what this question is trying to illustrate. I don't need a net force to change something's potential energy. I can just lift it at a constant velocity. That's still going to be work. I'm going to work against gravity. But I don't have to accelerate it to do that. If I do accelerate it, then I'm also changing its kinetic energy because I have a net force. Okay, everyone with me on that? So net forces change kinetic energy. Okay? If there is a net force, the object will accelerate and its kinetic energy is going to change. Okay, this is very much like the first one we did today with the ramp. Okay, so I want you to write this one down and give it a try. We might get it done today. We might have to finish it up tomorrow. Okay, so we'll go through that at the beginning of class tomorrow. From what I saw walking around, it looked like a lot of people figured that out. And that's not a super easy one. So if you did figure that out, good on you. If you didn't, that's not a super easy one, and we'll go through it tomorrow, okay? And I think you'll see how it works. It's a lot like the conservation of energy question with the roller coasters that you did in Science 10. The algebra is very similar, okay?